Hi class, welcome to the next section. It's the last section of chapter 12. You notice if you're following the textbooks, skipped a couple of sections, which is fine. This is the last section we're going to cover in chapter 12 before we finish out the textbook with chapter 13, in which I'm going to skip a couple of sections also. Today we're going to discuss the binomial theorem. The binomial theorem is actually super useful, very important to us. It helps makes a lot of things easier. If you've ever studied statistics or taken a stats class, you've actually used this in stats in a different way. However, we're not going to talk about the statistical application of this, but this is actually one of the central things in statistics. It leads to what's called the normal distribution, which is very important in statistics. Okay. But for us, what we're going to use the binomial theorem for is probably something different than we would in statistics. In stats, we would use this to find probabilities and things like that, which we can do here as well. If you move on from this class into a business calculus class, you'll use the binomial theorem a lot for calculating things like combinations and permutations. So we're not going to use that here. Here we're going to actually apply this binomial theorem into the general expansion of polynomials. So we're going to keep it more of a discussion of algebra and calculus rather than moving it into the combinatorics sort of direction and probability direction. Okay, so we're going to start off the discussion by talking about Pascal's triangle. Now, Pascal's triangle is super important in the formulation for the binomial theorem. It really helps us to be able to do a lot of the things that we want to do. It's going to actually be very fundamental for this section. We will talk about how to turn this into formulas, so we can just take a formulaic approach. But even from the formulaic approach, this triangle to me is actually way easier. Okay, so this is a way of finding coefficients for literally any binomial expansion. Now you might say, well, binomial expansion, anything that has the form of a plus b to the nth power, right? So again, Pascal's triangle connects the study of probability, combinations, and permutations with our study of polynomials, okay? The way that we create this triangle is with one row at a time. The first row has one value in it, and it is the value 1, okay? Each time you go to another row, we are going to add the values that are above our row, directly above whatever value it is that we're looking at, and those two values will add together to create our next diagonal entry, basically. Okay, so we're going to start off by calling our first row n equals 0. It's the 0th row. That starts off with 1. Then our next row, our second row, which actually is n equals 1, will be 1 and 1. Reason being is because there's nothing here. Plus 1 will give me 1. And then 1 plus the nothing here will give me 1. Okay. For n equals 2, I'm going to take the nothing I have here plus this 1 to give me my first value of 1. I'm going to have 1 plus 1 to give me my second entry. And then this 1 plus the nothing that's here to give me the next value of 1. Okay, so all along my triangle will always be 1 on one end and 1 on the other end, and all the middle values we find by adding the two values above it to create that, kind of like they siphon into this value here, right? So this value and this value funnels in and adds to this value. N equals 3 will be the same thing. I'll have a 1 and then a 3, right? 1 and 2 will give me 3. 2 plus 1 will give me 3. And then this will just be a 1. So if you notice, I have one element here. There's 2 in this row. There's 3 in this row. The third, n equals 3, has 4 elements in it. Okay, for n equals 4, I'll have 5 elements. It'll start off with a 1. The next one will be 4. The next one will be 6. Another 4. And another 1. You see how we have a lot of symmetry that's going on here? If I do n equals 5, I will start off again with a 1. This will be a 5. This will be 10. Another 10. 5. and another 1. So as we continue to progress, notice what's happening. These are all 1s. These are all 1s. This goes 1, 2, 3, 4, 5. This goes 1, 3, 6, 10. Notice the difference between these two numbers is 2. The difference between these two numbers is 3. The difference between these two numbers is 4. The difference between the next one would be 5. And there's just a lot of stuff that's happening here, right? So 1, then 6, 15, 20, 15, 6, and another 1. And we would just continue on in this fashion, literally forever, okay? Now you might say, well, that's cool. You know, there's lots of little cool things in here, Professor Williams, you know, that's nice. The 7th row has 7 elements in it. That makes sense because I'm just adding 1 each time. Oh, that's nice. You know, the first half is equal to the other half. If there's an odd number, then there's a central value before the symmetry. If it's an even number, then it just repeats twice. You know, that's cool. This is going 1, 2, 3, 4, 5, 6, 7, right? This does the same thing. This is going up by 2, then 3, then 4, then 5, then 6. That's cool. And I'm sure there's some other stuff that happens too, right? Here I'm going up by 3, and then by 6, and then by 10. So this has some sort of a pattern also. That's cool. But so what, right? So let's talk about how we use this, okay? These are the coefficients for a binomial expansion, okay? Think about 1, 2, 1. If I have x plus 1 squared and I multiply it out, these are the coefficients I have for that expansion. If I have x plus 1 cubed, these are the coefficients for that expansion. This would be x cubed, 3x squared, 3x plus 1. And it follows so forth and so forth and so forth, okay? So the values in the row are the coefficients for my binomial expansion. So x plus 1 to the 0 power, anything to the 0 power is just 1, right? X plus 1 to the first power is just x plus 1. So a coefficient of 1, coefficient of 1. 1, 1. Okay. X plus 1 squared is x squared plus 2x plus 1, or 1, 2, 1. Okay, 1, 2, 1. X plus 1 cubed is x cubed plus 3x squared plus 3 plus 1. 1, 3, 3, 1. Okay, x plus 1, 4. The fourth degree polynomial, 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. And if you don't believe me, go ahead and multiply that out the long way, plug it into a calculator, and see what you get out, right? So forth and so forth and so forth. So this is the binomial expansion of coefficient of 1, right, to the nth power. We can use this generalized form to expand any polynomial that has the form x plus a, or even with crazy stuff here and crazy stuff here. As long as it's 2 terms being raised to the nth power, we can use Pascal's triangle in order to do that, okay? So for instance, if I have x plus a to the n, then the a term multiplies times the x term. And it's going to increase in power starting from 0 all the way up to n, okay, for my a term. And my, for my x term, the a term is actually going to be decreasing in power, right? The x term decreases in power, right? It starts from 4, then 3, then 2, then 1, and then no power. My value of a, whatever it is, starts to increase, okay? And right now you can't really see it because it's all constants, but if I have, for instance, like a y here, you'll really see what I mean by that. And so here we'll have some coefficients which follow Pascal's triangle. So here everything was 1, so the different powers didn't manifest. But for the 2, we will have these same coefficients, but we'll also have powers of 2 that show up as well. So the first term here would be x squared. So x to the second power, 2 to the 0 power. Okay, so anything to the 0 power is 1, so that's why we won't see it. Next we will have 2. So remember, for a square term it's 1, 2, and 1. So this 2 is not related to this 2. This 2 is from the coefficient that's already there, from that expansion in the triangle, right? 1, 2, 1. So the first 2 that's showing up here is not coming from this progress I'm trying to say about a increasing in power. Okay, so 2. So the next thing that we'll see is x to the 1, because x will decrease, so it starts squared and then 1. Okay, and now our 2 is going to go from a 0 power to a 1 power, because the 2's will start to increase in power as x's go down in power. The next coefficient is 1. Okay, so here I didn't include it because it's not there, just like I didn't include it here. X is going down, so 2, 1, 0. The 2's are going to go up in power, 0, 1. This will be a 2 squared. So now if I actually multiply all this, this is just x squared. This is 2 times x, or 4x, and this is just 4, which we know is this expansion. We know x plus 2 squared is x squared plus 4x plus 2, because we do this all the time. Okay. However, x plus 2 cubed, we don't do all the time. Now, there is a general form for any binomial cubic, right? But following Pascal's triangle will be useful for us. So again, x's are going to decrease in power. X cubed, x squared, x1, no x, right? The 2's are going to go up in power. 2 to the 0 power, 2 to the first, 2 squared, 2 cubed. And we're going to have this 1, 3, 3, 1 coefficients. Okay, so this is the first term. Then I have 3. I'll have an x squared. I'll have a 2 to the 1 power. Okay, on the next term I'll have another 3. I will have an x, so 3, 2, this will be x to the first power. And I will have a 2, 0, 1, 2 squared. Okay, on the next term I'll have just a 1. I'll have x to the 0 power. And I'll have a 2 cubed. So if I multiply this out, x cubed, this will be 6x squared. This will be 4 times 3, so 12x plus 8. And if you go ahead and throw this into your calculator, you will get this exact value out. So this binomial expansion, super useful. You'll actually use this in calculus. It's actually, I took this from my calculus class that I took. I showed them the Pascal's Triangle, and it helped them a lot for a lot of the work that they had to do for the first part of calculus. Okay. So let's say we switch it up and we have a 2x minus 3y. So it's not just a standard x and not just a regular 2. It works the same way. This first term will be cubed, and this second term will be to the 0 power, the entire thing. So it works the same way. We still use the coefficients, but we just apply these rules in the same way. This term here starts with, in this case, a cube, and then a square, and then a first power, and then a no power. This term will also be in those products, and it'll start with the 0 power, and then a 1 power, and then a 2, and then a 3, and we will still have the coefficients 1, 3, 3, and 1. Let's go ahead and start to build this one piece at a time. So again, the first thing that I should have is this 2x being cubed, the entire term, not just the x, right? Or just the 2, the whole thing, coefficient of 1. Just like here. Then I have the second term to the 0 power. Okay, so this negative 3y, include the negative with it because it'll alternate signs. Then to that I will have 3 times this 2x going down in power, so squared. And this term, this negative 3y, going up in power, 1. Then one more 3. 2x, this was squared, so I'll just have a 1 power. This negative 3y is going 0, 1, so it'll have a second power. And then for the constant, the 2x goes to 0, coefficient is 1, and this negative 3y will go cubed. Okay, so all the ones that have a 0 power, I don't have to worry about because they all go to 1. So I'll have an 8x cubed. This goes away. I will have 4. Right, 2 squared is 4, and a 3 squared, so 9, so 36, and it'll be negative. So I should have minus 36 x squared y. Okay. Here I will have a positive 9 times 6, so 54 x y squared. Here this goes away. This will stay negative because it happens 3 times, so 3 cubed is 27. So I have minus 27y cubed. And if you want to double check, go ahead and throw this in your calculator or whatever other program you guys generally like to use when you're multiplying these things out when I tell you to do it by hand, and you can verify that this is in fact the expansion of this. And it's a simplified expansion. Imagine how much work it is to do this, to multiply it out 3 times and then condense it down. It is much faster to use Pascal's Triangle and this Binomial Theorem. Okay. Now there is a shortcut, although I think that this is pretty freaking short. To be honest, the shortcut is not really shorter. In fact, I think it takes a lot longer, but it is formulaic. It allows you to just plug everything into a formula, and it is very useful when you get into things like combinations and permutations and things like that, which is the binomial coefficient formula. Okay, so the coefficients follow this formula: n choose k, which is how this is pronounced, which has a formula for it. Okay, here n is the degree and k is the term number. So if I'm looking at a 4th degree polynomial, my first term would be 1. So I'd use 4 and 1, and that's how I'd get the first term, the coefficient for the first term. 4 and 2 would give me the coefficient for the second, and so forth and so forth. Okay, starting from 0. So 0, 1, 2, 3, 4. So n choose k has the formula n factorial divided by k factorial times n minus k factorial. Now factorial is probably new to you. I actually like using this formula because what you get to cancel out a lot of stuff, right? It's all about canceling things. However, calculating even one of these can take a lot longer time of sitting down and messing around than it does to just plug in one of these. This formula way, which we're still discussing it, so if you're like, Professor Williams, what are you talking about? I haven't discussed it yet, so don't worry about it. Using this method is really nice when you have very large values. So if I had like 2x minus 3y to the 8th power, for instance, that's a lot of this stuff to do. This might be a little faster, or like to the 50th term or something like that. This formula will be easier. So first, let's talk about what factorial is. Factorial is very, very common in mathematics. Again, you probably haven't seen it yet, but it does show up a lot in Calculus 2. It's actually kind of everywhere in Calculus 2. So factorial just means you multiply all the values, integer-wise, positive integers, up until your value n. So for instance, if I say 5 factorial, 5 with this exclamation mark, 5 factorial is 5 times 4 times 3 times 2 times 1. You do not include 0, because if I included 0, everything would just be 0, right? So 5 factorial is your number, and then minus 1, then minus 2, then minus 3, then all the way down until 1. The definition of 0 factorial is 1. Okay, so if you ever see somewhere, for instance, if I say choose 0, you would have 0 here, 0 factorial. 0 factorial is not 0. 0 factorial is 1. Okay, so the definition of n factorial is n times n minus 1 times n minus 2 times n minus 3, so forth and so forth, until you get to 2 times 1. Okay, so all the way down to 1 is how n factorial works. So for instance, 4 factorial is 4 times 3 times 2 times 1. You do not include 0. If I have n minus k factorial, I would do this math first. I would do this subtraction, and then whatever number I get, I take its factorial. Okay, so that's how that works. This is very, very common. You're going to see this again in combinatorics and in statistics if you ever take a stats class. So here I'm going to get 24 because that's 6 times 4 times 1. 5 choose 3 means that, again, the top number is on top, the bottom number is on bottom, and on bottom I have whatever the difference between these two values is. So I'll have 5 factorial on top, 3 factorial on bottom, times 2 factorial. Okay. So 5 factorial is 5, 4, 3, 2, 1. 3 factorial is 3, 2, 1. And 5 minus 3 is 2 factorial, 2 times 1. But if you notice, I switched them around. And you might say, why did you do that? Because notice I have the 3, 2, and 1 all lined up. So that's why I put the 3 factorial in back instead of in front like it is in the formula. So I did switch their positions, Sorry, I know that that's probably confusing to you guys, but I did that so that we can see that we have them lined up. Because remember, when you have multiplication only, no addition, no subtraction, you get to cancel stuff. So instantly I know 3, 2, and 1 cancel. And I'm left with 5 times 4 over basically 2. Well, hey, guess what? More stuff gets to cancel. And this simplifies to just 10. So that's the thing with factorials, is generally a lot of stuff will cancel, right? And you're left with some set of multiplications, sometimes 2 numbers, sometimes only 1 number, sometimes 5 numbers are left. It really just depends on the values that you have here. But this is the way that 5 choose 3 works, right? N choose k. So x plus a to the nth has the expansion of x plus a to the n. So we have x to the n, because I'll have 5 choose 0. I'm not going to go through the formula, but it'll always be 1. Okay. Then we're going to have n, x to the n minus 1 times a. So again, notice x is going down in power. A is increasing. Then we'll have n choose 2. The reason I only have to write n here is because we already know from the expansion that this is equal, just come back up to it, it's equal to the row that I'm on, right? If I'm on the second row, the second number is 2. When I'm on the third power, the second power is 3, right? When I'm on 4, the second coefficient is 4. It just works out that way, okay? So let's come through all of this. All right. Here we'll have n choose 2. So n choose 1 will just be n. N choose 0 will just be 1. N choose 2. And then this is the power that we have for this one. So forth and so forth. And then it repeats all the way to the other side. So again, this can be kind of confusing, which is why I generally don't work with it. And I'll just use that Pascal's triangle. Again, this is helpful when you have something very large, right? So if we want to generalize this, these values are coefficients. C1, I'm sorry, C0, C1, C2, etc., etc. Now, when I have something times this x, then, you know, that changes things a little bit as well. But for the basic one, right, the basic expansion of the nth row of Pascal's triangle will look like this, right? Each Ci is given by this n choose n minus I, where I is whichever value it is that we're looking at, the 4th term, 5th term, etc.